Not really.
Oh, no? Yes. No. I'm confusing you. I'm getting the wrong answers what I'm doing. Oh, I know what I'm not doing. Smart alecky kids. Okay. I'm not even following my own advice. It seems to be .070. Quit making fun of me. So this is 7.5, right? Times 10 to the minus 25th. And now divide by. There we go. I'm much happier with that answer. So 8.3. There you go.
Baby white
Yeah.
flavored jelly beans.
Ew.
The birdie box.
That's why I am. Are you talking about the Harry Potter one?
Yeah, the birdie box. They have like baby wipe and earwax and vomit.
Never ever try those.
Baby wipe.
I got one
Now, is that
package
used?
like 5-6 years ago, and yeah, it was like me, my brother, and cousin.
I'm possibly good with a nice toffee.
I never.
Alas, earwax.
Earwax. I
Huh?
never got any of the disgusting ones, but instead what
Times 10 to the 5th. Yeah, there you go. You got it. Yeah.
we tricked one of our cousins into
Yeah.
eating one.
Isn't that funny? This thing is like about as powerful as like a pocket laser pointer.
Yeah, I know. Why is it like?
Because it's not solid state.
Oh.
It's got actual tube of neon in there.
Wow.
Yeah.
So don't drop it.
Cool.
Drop it.
Do you guys know how lasers work?
Not really.
Nope.
They kind of like magnets.
It's got a neon. We still have stuff to do. Don't put your stuff away, boys and girls.
Still whiteboard.
The way this thing, no more whiteboards, but the way this thing works is it's got a little tube in there. Inside that tube there's neon and it pumps. It's like a standing wave, and it's pumping that standing wave up by just pumping electrical energy into there, right? Now imagine a standing wave like that coil like that, right? Of me shaking that, right? It's got some standing wave set up in there, and all it does is on the front side it's got half silvered mirror, so some of the light can get out. That'd be like having that end be not just the countertop, but a continuing slinky, right, going that way, right? And somehow some of it reflects. So they put a heavy object on there, but some of it can get out, right? Well, if it's coming from a pure standing wave, isn't the stuff coming out all the same wavelength, all the same frequency? Yeah, it's a beautiful thing, right? It's light amplification through stimulated emission of radiation. And they'll just pump each other up. The photons themselves make the atoms give off the wavelength. Well, any resonance phenomenon like that is you can pump it up to really, really high energies, right? Okay. So the final thing, and this is wafer thin, if you ever get to write a paper for like, I don't know, some physics, course that you take, there was the Einstein-Bohr debate. Bohr believed in all this non-determinism, quantum randomness, Heisenberg uncertainty principle, and Einstein is famous for saying that he does not believe God plays at dice. And basically, he either didn't like the Heisenberg uncertainty principle or he didn't like complementarity. Complementarity was this notion that light would act as a particle or a wave, but never both. Or electrons would act as a particle or a wave, but never both. And what Einstein would do is he would go to a conference. This is Wolfgang Pauli. That's Bohr on the side there. Otto Stern, Lisa Meitner. Einstein, is he there? I don't see him at this one, but he might be there anyway. But he's busy getting his challenge to Bohr, right? He would challenge Bohr. So, for example, what Einstein said, this is a Gedanken experiment. Nobody could do this. It just means thought, right? You send an electron beam to this thing, and it's going to make an interference pattern. That's a wave property, yes? Only waves do this, okay? And what he does is he sets up a light a little light beam across here, kind of like a burglar alarm, right? And if the electron goes through this side, we'll know it did. Isn't it acting like a particle if it chooses one or the other? If it's acting like a wave, it somehow goes through both in some weird way that we don't really understand. If it acts like a particle, it goes through this one and not that one. So Einstein sets up a light beam and he says, look, I can both get an interference pattern and I can know which one it went through. Yeah? Therefore, your theory is a piece of crock. Yeah? Yeah? Well, what's the problem, you know? Well, you know, like, well, he'd go for a walk, right? So here he is walking. He liked to walk outside and talk, right? Well, he came up with it, you know, this one. And there's several of these. There's a light in the box and several other ones that are fairly accessible. His answer is this. If you have a light beam shining across there, what's it going to do to an electron that goes through there? Is it going to observe it and not change anything about it? Or is it going to change the crap out of its velocity? If you change its velocity, don't you change its wavelength? And if you change its wavelength, isn't it not going to interfere? So by observing the electron going through this slit, you're going to destroy the interference pattern. If you want the interference pattern, you just can't observe the electrons. Isn't that weird? And every attempt, by the way, to do this, to observe wave behavior and particle behavior, is always thwarted by something like that. Okay, as far as we know, complementarity, Heisenberg uncertainty are just these things that are deeply rooted as part of quantum reality, of quantum nature, right? And so you basically have several kinds of physics, right? Okay. Newtonian is this works for big stuff, yeah? Relativity is just basically a classical theory, but it works. You have to change it slightly for speeds close to the speed of light. And if you're going to deal with small objects like electrons that could be buffeted about by photons, yeah? Think, will it be changed by a photon, right? We've got to use quantum mechanics, you know? So this is, yeah, there it is.